Welcome back, students. Let's move on to 6.2. In the previous section, 6.1, we talked about the angles and measurement, especially the radian angle, and we started with a circle centered at the origin, x squared plus y squared equal to r squared, and then we defined the angle as the counterclockwise arc length from the initial point r comma 0 divided by the radius. Consequently, as long as we have the same terminal ray, we have the same angle even if we have different arc length, as we see over here in this visualization. With two different radii and two different arc lengths, we still have the same angles because they share the same terminal ray. If the rotation is clockwise, then the angle is negative. And here's the definition again. Arc length over radius, actually counterclockwise arc length over radius. But if we ignore the direction and positive or negative, then we have just geometrical arc length over radius and a geometrical angle difference. So S equal to r theta, the arc length formula comes. And of course we went through area formula as well, 1/2 r squared theta. Conversion between degree angle and radian angle was easy. Pi over 180 degrees or 180 degrees over pi, depending upon what to change to what. Okay, that was a quick review. And then now let's move on to the trigonometry of right angles. And this is the definition of the trigonometric ratios of the acute angle, where the angle is between 0 and pi over 2, or equivalently in terms of DMS angle, between 0 and 90 degrees. Because I have extension in my mind, I do the picture in the circle of radius r, even though in this particular case we're going to get only the first quadrant. Here we go. X and y are horizontal and vertical, but in terms of the central angle, x is the adjacent and y is the opposite. R is the radius of the circle, but in terms of this triangle, which is highlighted in red, that's its hypotenuse. And the trigonometric ratios, sine, cosine, and tangent, are defined like this. Sine of theta is opposite over hypotenuse, y over r. Cosine of theta is adjacent over hypotenuse, x over r. And tangent of theta is y over x, opposite over adjacent. There are three more trigonometric ratios, cosecant, secant, and cotangent, but they are less important because cosecant, cosecant, and cotangent are reciprocals of sine, cosine, and tangent respectively. Hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite respectively. Okay, now that we talked about the definitions of trigonometric functions, let's talk about some special values. Oh, actually, before talking about the special values, let's talk about one property of trigonometric identities. Trigonometric ratios. Sine of 2 pi over 2 minus theta is equal to cosine of theta. Cosine of pi over 2 minus theta is sine of theta. And tangent of pi over 2 minus theta is cotangent of theta. And those are actually coming from these observations. Okay, let's suppose we have a triangle, right triangle like this, ABR, and the angle associated to point A is alpha in terms of radian measure, and the angle associated to capital B, point B, is beta in radian measure, then the sum of the angles in radian measures must add up to pi over 2. As a matter of fact, if you use degree measure, then the angles must add up to 90 degrees. These two plus another 90 degrees will be 180 degrees. Remember, the internal angles of triangles must add up to 180 degrees total, or pi in terms of radian measure. So what do you get? Flip alpha to the other side, then beta is pi over 2 minus alpha. And then let's look at this. If you take B as your standard angle, then what is sine of B? Sine of B is opposite over hypotenuse, isn't it? And opposite for B is x. And then hypotenuse is, of course, r. And that's equal to cosine of alpha, because with respect to point A, x is adjacent. Now how about cosine of beta, the top angle? So that's adjacent over hypotenuse. What is adjacent in this case? It's y. Because B is on top, adjacent is actually y. So we have y over r. But then again, if you look at from a viewpoint of the point A, angle A, then y is the opposite. So we have sine of alpha. Finally, let's move on to tangent of beta. That's opposite over adjacent for B. So opposite is x, adjacent is y. Now if you look at in terms of angle A, y is opposite, x is adjacent. They're reversed. So we have adjacent over opposite. So that's cotangent. So by looking at these angles in this triangle, we can find out these relationship between the complementary angles. Alpha plus beta is pi over 2, or in terms of degree measure, capital A plus capital B is 90 degrees. In this case, sine of beta is same as cosine of alpha. Cosine of beta is equal to sine of alpha. Tangent of beta is equal to cotangent of alpha, and so on. And then what is beta? Beta is pi over 2 minus alpha. So we end up with these three. Simply rewriting these alpha into theta, we end up with the original form here. Relationship between trig values of complementary angles. So that was a nice proof of trigonometric identities using geometry. Okay, let's talk about a little bit more examples on geometry. Using those, let's find out some standard trig values. And let's begin with sine of 0 and cosine of 0 and tangent of 0, which is actually trivial. And it's actually stupid. So this is what we get. Is it a triangle? It's just a line segment because angle is 0, so we end up with a degenerate triangle. It's a line segment. Height is 0. It doesn't go up because angle is 0. So what do you get? 0 over r, so sine of 0 is 0. And how about cosine? The triangle, if you call it a triangle, does not go up, so adjacent and hypotenuse are the same. So x over r is 1. And tangent is also 0. Y over x, y is 0, x is same as r. Degenerate triangle. That kind of strange, but yes, works that way. And here's more interesting situation. And sine of pi over 6, or 30 degrees, or cosine of pi over 6, again 30 degrees, tangent of pi over 6, we have 1/2 square root of 3 over 2 and 1 over square root of 3 respectively, and they all come from this triangle, 1 square root of 3, 2 triangle. Why? Well, let's go to a geometry, and it all comes from this observation here. We begin with a equilateral triangle with side 2, It's an equilateral triangle, so all the internal angles must have the same magnitude, so they're all 60 degrees. So 60, 60, 60 add up to 180 degrees. And then take a bisecting line of the top angle, generating 30 and 30 degrees. And because of the symmetry, this bisecting line must bisect the bottom side perpendicularly, generating a triangle, a pair of triangles that are congruent. In the left-hand side, we have blue triangle with side 1 and 2, and then 30 degrees and 60 degrees. And then in the right-hand side, we have this pink triangle with side 1 and 2 with 60 degrees and 30 degrees and 90 degrees, and a height which is not really known yet. How do you find out the height? Well, we can find out through the Pythagorean rule. Because 1 squared plus h squared is equal to 2 squared if you use the Pythagorean identity, or Pythagorean theorem, excuse me. Hypotenuse is 2 and horizontal is 1 and height is unknown. Okay, how do you find out my h squared? Is 2 squared minus 1, that's 3. So taking the square root, we add h equals the square root of 3. Of course, we are talking about geometry, so negative square root of 3 doesn't make any sense. That's how we can find out a height of a equilateral triangle of side 2, excuse me, with square root of 3. Consequently, we ended up with a standard triangle with 30 degrees and 60 degrees with side 1, square root of 3, and 2. And you can use that triangle positioned this way so that we have 30 degrees. And then we can answer sine, cosine, and tangent values using opposite over hypotenuse, adjacent over hypotenuse, and then opposite over adjacent, respectively. We can do the same thing with angle pi over 3 or 60 degrees. The same standard triangle positioned this way so that we have 60 degrees on the central angle. Again, 1 square root of 3, 2 triangle. So sine value, cosine value, tangent value can be obtained by the triangle. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, respectively. Now, pi over 4 case is a little bit different. This time we have to start with a right isosceles triangle here. And then if we use Pythagorean rule, Pythagorean theorem, 1 squared plus 1 squared is hypotenuse, which we don't know. Consequently, what do we have? R is square root of 1 plus 1, square root of 2. And that's how we get this triangle, 1, 1, square root of 2 triangle. So if we put that here, then for 45 degrees or pi over 4, we can inscribe this 1, 1 square root of 2 triangle, and consequently we get the sine, cosine, and tangent values as 1 over square root of 2, 1 over square root of 2, and 1 over 1 respectively. Final case, when we have precisely pi over 2, well, we have another degenerate triangle or line segment here, and this time horizontal is 0, adjacent is 0, so we have sine is r over r, 1, cosine is 0 over r, so 0, tangent is 1 over 0, so it's undefined. So tangent function, tangent can be rather strange, it's undefined for 90 degrees.